Hi, this is going to be part 3 of the video series on induction, and in this part I'm only going to go over 2 more examples. The first one is an example where we imagine we have a long straight wire that carries a current, and then I have a loop of conductor, another loop of wire essentially. There's no current in there right now. But I imagine I take this loop and I move it sideways to the right with a certain speed v. Now, why is this example going to, or why is the situation going to create a current in this loop? Well, we know that a straight wire carrying current creates a magnetic field, and we in fact know what a magnetic field is. And the magnetic field around it created by this wire gets weaker as you go further away. So by moving this wire, this loop of wire to the right, I'm moving it from where there's a fairly strong magnetic field to where there's a weaker magnetic field. So that'll change the flux inside this loop. This example is a little bit more complicated than previous ones because the magnetic field is not constant in strength. Right? It's not constant in strength, not just in time, we've had examples like that, but it's not constant in strength from here to here to here. In fact, it's not constant in strength everywhere inside that loop, right? This side here is going to have a stronger field than this side over here. So we're going to apply what we know about Faraday's law, apply to this situation. It'll be a little bit more complicated mathematically, but in principle, everything will be exactly the same as before, just more involved math. So let's get started. So the wire we're going to assume, or this loop, right, it's a rectangle. It has a length L, and then we're going to call this the length from here to here, and the width W. The whole thing moves with speed v to the right, and I call the distance of this side here. And from the wire I call it r. So this side here is going to have the distance r plus w. So the first thing you want to figure out is how does the speed relate to those other variables. Now of course L and W, they stay the same. The thing that v changes is r, right? The distance between the loop, or this side of the loop, and the wire. So v equal to dr dt. It's something we might need down the road. Okay, so let's figure out what is the flux. So the first thing we want to figure out is which way is the magnetic field. So curly hand rule, right? The current is up. I do it like this. Current is up, so my fingers on this side of the wire, they're pointing down. So while I'm in here, the magnetic field points straight downwards into the page. And of course, it's going to be stronger here than over here. And we know what it is. The strength of the B field is mu naught times I over 2 pi r. Just notice we've had it before. Maybe you've done the calculation using Ampere's law to actually derive this, but we can just take it right now as a given. So the distance changes with r. Oops, I need to be careful here. I say r. Of course, do I mean the same r as this? Well, I mean the distance from the wire. So let me sort of call this maybe, we call it little d, so don't confuse it with this r, right? D, distance from wire. Of course, we know this, we just don't want to get confused once we're in the middle of all the algebra. So let's figure out what is the flux. Now you might say, okay, the flux is the area times the magnetic field, right? Fair enough. The problem is the magnetic field inside this loop is not constant, right? It's different, stronger here than this over here. Maybe I can actually indicate this by having a couple more of crosses over here, so you can see it's a bit less over here than it's over here. Okay, So how are we going to figure out what the total flux is? Never mind the change in flux that we ultimately are trying to find, right? The rate of change of flux. So it goes in Faraday's law. Well, what is the flux right now at this time? So the way we're going to do this is we're going to say, well, I can't just take total area times the magnetic field, because which magnetic field value should I choose? The average? That's not going to be exact. Because it's not a linear function, it's 1 over d. So here's what we're going to do. We're going to split this this rectangle into tiny little strips, like this. Each strip, the magnetic field is about constant, because each strip, everywhere along one strip, the magnetic field is the same distance from the wire. So I hope you agree with me that pick any one of those strips, say this one here. Imagine this strip is thin enough, then the magnetic field along the strip is going to be constant. Then I'm just going to add, I'm going to figure out the flux for each strip, and I'm going to add them. Let's work this out. So phi is equal to, well, we're going to call the area of one such strip, it's a little area, so we're going to call the area of the strip dA. Of one strip, call it dA, because it's tiny, imagined infinitesimally small, if it's just super thin, infinitesimally small fraction of the total area A. So then all we're going to do is the flux through one strip is going to be the B dot dA, and the angle here is, of course, 0. The angle between the magnetic field and the flux sticking out of the surface is 0 in the same direction, so there's no cosine of anything, because the cosine of 0 is 1. So this is one strip. We're going to add them all up. So if you add an infinite number of infinitesimally small bits, we're going to call this an integral. Right? Integral, remember, this means take the sum of whatever comes behind it, and in our case, we're taking the sum of b dot dA. The sum is going to be taken over the area of the loop. So how are we going to put that into more concrete terms? Let me continue my calculation down here. Well, let me, so I need to label my strips, right? Like 1, 2, 3, 4. Of course, that's not going to get there if I label them 1, 2, 3, 4, because I've got an infinite number of them. So I'm just going to label the strip by how far it is from this edge here. So if this, you like, is another variable x. So x denotes the distance from here to wherever, like whichever strip I'm currently looking at. Make sure you understand what x denotes. Because we're going to sum over different values of x. X equals 0, x equals 1 millimeter, x equals 2 millimeters, and so on. So I'm taking the sum from x equals 0, means I'm on the left edge, to x equals, what's the final x value? When I'm going to stop here, that's when x is w, the width, because it's gone from here all the way over here. So the x value for my last strip is equal to w. I'm going to take my sum from 0 to the w, my x values. Now, what is the magnetic field? It's going to be mu naught I over 2 pi. Now, what do I put in for the distance? Well, if you're here, say, the distance from the wire, it's not x, it's not r, it's r plus x. Right? So remember, you interpreters always think, well, what is the actual distance that I'm plugging in here? So maybe r could be used to denote some kind of other quantity like it is here. So don't blindly plug in. Like, think about what you're doing. The distance from the wire for an arbitrary point here is r plus x. Of course, you could have labeled the quantities differently. Right? You could have r go to the center of this, in which case your limits would be a bit different and this expression would be a bit different. You're going to get the same answer. And of course, the A, what is the little area? Well, it's going to be the length times dx, right? The area of one of those is the length of it times the width, and the width is a small change in x as I go from here to here. This is going to be L dx. So again, with integrals, even if you know how to do integrals from a calculus course, the hard part in physics is often understanding really what they mean, how to set them up. And to some extent, that's not something you're going to learn in a math course. You're going to learn this in a physics course, where you're actually using it for something useful. Now, this is a very simple integral to evaluate, because really it's just that the x only appears here, your integration variable. So 1 over, so technically how you might do this is that you do a change of variables, you define u is r plus x, and so on. Let's do it. Why not? Let's do this explicitly. We're learning something in the process, right? So I'm going to define change variables. I'm going to say u is r plus x. My new variable, I'm going to call it u. So du is just dx. A small change in u, well, r doesn't change. A small change in x. So my flux becomes the integral of mu naught I, and I put the L up here, divided by 2 pi u. That's why I made that change, right? That choice was to simplify this. Du. Okay, but neither. Oh, what are the limits? Well, x equals 0 means u is equal to r. X equals w, that was our final limit, means u is equal to r plus w. Okay. Make sure you understand every step, because these are techniques that you should be able to perform. And these are techniques that they should become part of your sort of toolbox as a engineer or scientist. All right, so we can evaluate this, right? This gives me, let's work it out. Well, mu naught I L over 2 pi is just a constant. And then 1 over u du becomes log of u. That's evaluated between r and r plus w. So that's going to be mu naught I times L over 2 pi times the log of r plus w over, oops, not w, that's a mistake, over r. So like this. Now, what have I used here? I've used that log of a minus log of b is log of a over b, right? That's how I end up with this integral. It really gives me log of this minus log of this, but I rewrite it like this. The reason for it, that log of r is sort of a strange quantity to have, because the log of something in meters, right? What does it mean? What is a log of meters? Well, this thing here doesn't have units because it's a ratio of two lengths. So this is more sort of physically sensible, as it were. Okay, so now I have an expression for the flux. Am I done? No, because what I want to find is the rate of change of flux, right? That is what Faraday's law says. The potential, the EMF induced in this is the rate of change of flux, right? Faraday's law says the induced EMF is, the magnitude of it anyway, is d phi b dt. So in our case, that is equal to the absolute value, I'm not going to write it down, of d dt, right, of mu naught I L divided by 2 pi times the log of R plus W over R. Okay. Now, lucky for us, this whole thing is a constant. This whole thing just goes out front. I'm going to get mu naught I L over 2 pi times d dt, the log of R plus W over R. Alright, so, okay, this is a constant, that's fine. This thing, how are we going to value this thing? Well, W does not change, right? W is a constant, but what changes is R, right? Remember, R denoted the distance from here to here, and that is changing, and we call the rate of change of R, we call that the speed V. So let's evaluate this. So you should know how to take the derivative of a log function. We're going to get 1 over the function times the derivative of the function. So I'm now going to use the chain rule, that d dt of the log of a function f is equal to 1 over f. It's ddf of this times df dt. Right, so hopefully it's something you remember from your calculus course. Okay, what are we going to make that equal to? Or what does this make, I guess? Mu naught I L over 2 pi times 1 over this. Now 1 over, let me write it out. I'm going to skip a step, let me write it out. 1 over the thing inside the log times d dt of the thing inside the log. And again, I should just be able to give you the answer. You should just be able to take it from there, but, you know, practice makes perfect. Let's do this. So, what does this make? Mu naught I L over 2 pi. Now I can just simplify this a little bit by writing it like this. And what does this make? Well, actually, I can rewrite this in a much nicer way, where I say this is R plus W over R. It's just 1 plus W over R. Right? So that makes this look much nicer, because d dt of this is easy, right? d dt of 1 is 0, and d dt of W over R is going to be W times the log. Oops, what have I done? Not integrating. It's minus 1 over R squared. Right, taking the time derivative of this, but I've rewritten this as this. Right, you're going to get this. Now we just simplify this a little bit. I'm going to get mu naught I L over 2 pi. Now there's a minus sign here, but I guess I should have kept the absolute value every step of the way. Sort of a pain to write, makes the whole thing look very sort of in your face, whole expression. Guess you could do it. So the minus sign just now goes away because we take the absolute value. R cancels R, and we get W over R plus W. Right, one of this is squared here, cancels this thing up there. Alright, so that is our answer. Right, that is going to be the strength of the induced current. And now notice that this induced current is going to get less and less as essentially 1 over R squared, as R times R, right, in the denominator here. So the current induced in this loop changes rather quickly, right? It's initially there's a lot. If you go at constant speed, hold on a minute. Did I make a mistake? Yes, I did. Hopefully you caught the mistake that I made. I took ddt of this, but what I valued was ddr of this. This line here. Oh dear me, dear me. Should have, of course, this times dr dt. Forgot this part here. Why? Let me just annotate this for you. This part here, this was ddr, so I'm writing ddr of this, of 1 plus w over r, but I don't want ddr, I want ddt, so I need to multiply this by dr dt, right, by the chain rule. Again. I was like, something seemed wrong here, right? dr dt. Hope you can see why, right? As I said, ddr of this function gives me this, but I want ddt. So with the chain rule, ddt of this is dr dt times ddr of this. Let me make it even clearer. I'm going to write d dt as dr dt times ddr of whatever comes next. Because r is the only variable changes with time, so I'm allowed to do that. Okay, so that means I've got dr dt, but what's the r dt? The r dt is just the speed. Okay, now if the speed is constant, right, then still the induced current falls off as 1 over essentially r squared, sort of 1 over r squared plus r w in the denominator. Kind of a modified r square law, right? Assuming I'm going at a constant speed. Okay, so this is my induced EMF. I here is the current in the original straight wire, right, not in the loop. Let's ask, which way is the current induced in the loop? Which way does it go? Is it going clockwise or counterclockwise? Well, to do that, let's use Lenz's law. So which way? Well, I'm going to use Lenz's law to find out. So, how are we going to do this? The B field is down. The existing B field due to the wire over here. B down. So I can say that the flux points down. In a way, flux, B field are kind of the same here in terms of direction. If the B field points down, then I'm saying the flux points down. B down, flux down. So the flux, though, is becoming weaker. Flux is getting smaller as time goes by because the loop is moving away towards a smaller magnetic field. In fact, we've worked out it gets smaller as essentially 1 over r squared. So the further I'm away, the weaker it is. Bigger r, smaller EMF. Flux is getting smaller, so the change in flux points up, right? So imagine if the flux was a downward vector, I've got a smaller downward vector a little bit down the road, a little bit later, then the change in flux was in the opposite direction. Right? I went from this flux to this flux, so I had the change in flux was this. Okay, so that means the induced field points down. this is lens slope, or lens slope. By lens says the change in flux points up, the induced current creates downward flux. So now, okay, which way is that? Is it clockwise or counterclockwise? Well, if I go clockwise around it, then I go like this. And indeed, inside the loop, like my thumb traces along the outside, inside the loop, then my fingers always pointing down. Whereas if I went counterclockwise, then inside the loop, my fingers would always be pointing up. And so the current induced must be clockwise. Alright, so we figured out the strength of the EMF, and we figured out which way the resulting current flow. Could we have worked this out differently? Yes, we could have. We could have treated those two wires, or like all four sides, strictly speaking, of the wire separately, and said, okay, I'm moving a wire through a magnetic field that's changing. Well, can I find the force, like the potential difference from here to here, from here to here, and from here to here, and from here to here, essentially doing 4 times a calculation on motional EMF. It's not a fun calculation to do, and you've got to be careful about directions. For example, those two wires, right, will have opposing EMFs. But this one is going to have a stronger EMF than this one because the magnetic field here is stronger. But they're moving with the same speed. See if you can work it out in that other way. By thinking of this loop as 4 separate wires, you work out the motional EMF for each one of them. You should get the same answer. Alright, that was the first example. Now let's come to the second example. This is the second example. So imagine I have a rectangular loop. And maybe the loop is hooked up to something else. I'm not going to worry about that. And that loop is rotating. Maybe there's somebody cranking a handle over here, spinning this loop. So you really got to think 3D here. Imagine the magnetic field is down, right? And then right now this is flat in the plane of the paper. Let's see if I can use this blue thing here. And then I'm going to go like this. The magnetic field is down the whole time, and this thing is spinning. What does it say? Some memory reminder for myself to do some paperwork. Alright. So that's the idea here. Now if I look at it from the front, meaning from front I think I'm standing like where my pencil tip is right now, looking this way, I'll see it do this, right? So right now it's kind of flat, and a little bit it'll be sort of bigger as it's vertical, and it keeps spinning. Actually I do the arrows up here, even though they point down, I guess I've got my head upside down. If you look at it from the side, so I'm looking at it from this direction here, I'd see something like this. I'd see maybe those 2 bits of wire, they come straight towards me here, right? And this whole thing is spinning like this. Okay. Let me call this angle here theta. Of course, that theta will change with time. Okay, so I want to figure out what is the flux through the loop. Now the loop has a fixed area A. And I assume the magnetic field, I'm just going to call it B, it is constant. So because this thing is rotating like this, the angle between the two is going to constantly change. So let's set this up. The flux at any one time, phi B, is equal to the area times the magnetic field times the cosine of the angle between those two. Now the angle between those two, strictly speaking, right, is this angle here. Let's call this alpha. So use theta for this one. Cosine alpha. And I can just leave everything in terms of alpha here. I don't need to worry about this. I'm going to use this angle here. That's AB cosine alpha. Now, if this loop just sits there, nothing changes, this is constant, right? Let's assume alpha is rotating. So that means it depends on time, right? This whole thing is spinning. If it's spinning at a constant rate, I might write down the rate of rotation as omega. Omega is the the radians per second times the number of seconds. If it's 2 radians per second, it means the alpha is 0 at time 0. At time 0.1, it's 0.1 times 2 radians. At time 0.2 seconds, it would be 0.2 times this value is 2, so 0.4 radians and so on. Right? So it's just a linear function of time. The angle is a linear function of time. So my flux is AB cosine of omega t. Because this thing keeps going up, it's going to go from 0 to 1, 2, 3, 4, 5, 6, and it's at 2 pi, which means it's on a whole rotation, but that's okay. It'll just keep going, right? If it's gone this angle in here, this thing inside the cosine is 6 pi. This means it's going to run 3 times, which is going to happen if we just wait long enough. Okay. So what I care about is the induced EMF. Induced EMF is by Faraday's law d phi b dt, which is, well, these are just constant in this case, A, B, they're also positive, so I can take them out of the absolute value thing. Then I get d dt of cosine omega t. Okay. So I can evaluate this, and I get A, B, and the ddt of this is going to be omega times sine omega t. Right? Hopefully you know how to differentiate a cosine function. Cosine becomes minus sine, excuse me, but it's okay. I'm going to take the absolute value, right? Leave this here because sine could be positive or negative. And the thing inside the cosine hops out front, right? You take the derivative. So hopefully you know that. So this is going to be the induced EMF, which is interesting because this thing itself varies with time, right? It goes between +1, -1. So really what I'm going to get is, if I worry about direction 2, it's going to do something like this. With time, the EMF as a function of time is going to oscillate. Right? Of course, strictly speaking, if I take the absolute value, I'm always going to get positive numbers. But what you could double check is that the direction is used constantly flips back and forth based on whether it's going essentially like this or whether it's on the other side. Right? So in one rotation, you're going to get an EMF one way, and then back to 0, and then the other way. So now the current would flow the other way. So current goes one way, the other way, one way, the other way. And thus so, the strength of it follows the sinusoidal shape. Call this an AC current. So in this kind of setup, we've created an AC current. So what you could imagine is somebody here cranks this thing and maybe hooks up to a light bulb. We're going to get the light bulb will glow. This light bulb doesn't care that the current goes one way and then the other way. It's still the same principles apply as before. In fact, if this happens fast enough, right, you're not going to see the low current in between, because the light bulb just stays hot, so it glows continuously. It doesn't have enough time to cool down. If you crank it very slowly, you might see it go dimmer in between. We'd also imagine, instead of cranking this with your hand, you have some kind of maybe water wheel here, or a big windmill that does the spinning, and you've created essentially a power station right here. So this was an example where the angle changes. Here the angle was a function of time, right? So what did we get in this case? We got an oscillating current, an oscillating EMF. Alright, so that's it for those examples. For induction, the rest is really applying it to more examples. You will be able to do that in the homework. And once you've mastered this stuff, we can take it a step beyond, thinking about some further implications, among them, for example, the existence of waves, electromagnetic waves, such as light and gamma rays and microwaves and all those kinds of things. Alright, that's it. Hopefully those examples helped, and I will see you in class.